Hi everyone. So we are taking a look at our very last section that we're going to cover, which is going to be section 9, and that's covering cardiac output. So we're going to take a look at, we're going to define cardiac output, we're going to take a look at something called cardiac reserve, and then we're going to go into the different variables that are going to influence cardiac output. So let's first start out by actually defining cardiac output so we know exactly what it is. Cardiac output is going to be the amount of blood pumped by a single ventricle in 1 minute. And it's always going to be given in liters per minute. And really what it's going in and doing is it's measuring the effectiveness of the cardiovascular system. It's going to determine how much perfusion there is. Remember, perfusion has to do with the amount of blood that's being delivered to the different tissues in a certain amount of time. And this, if you look at that, is very similar to perfusion, because if your cardiac output is going to change, so is your perfusion. And we'll look at how cardiac output is actually going to increase whenever individuals are exercising. It makes sense because when you're exercising, you want more blood that's going to your tissues. You need more perfusion. So yeah, this would definitely increase while you are exercising. Two main factors are going to determine cardiac output, and they are going to be heart rate and stroke volume. So normal heart rate, we're just going to go with average heart rate, is going to be 75 beats per minute. I'm just going to put beats per minute. And then if we take a look at what normal stroke volume is, normal stroke volume is going to be, and it gives you an idea of what it is. It's a measurement of course, a volume. So this one's going to be 70 milliliters per minute. And again, this is just average. This is going to be different from individual to individual, like we're going to talk about here in a second. And if you do some fast multiplication, that is going to give you 5,250 mils per minute. And that is going to be equivalent to 5.25 liters per minute. Think about that. You have roughly a little over 5 liters of blood that's pumping through that ventricle. And it says one single ventricle because remember, we talked about how the amount of blood is going to be the same that's pumping from both ventricles. So there's no sense in just saying, you know, it's going in as the right ventricle or the left ventricle. It's going to be the same amount. But 5.25 liters per minute, remember that the volume of blood in an individual is 5 liters. Males were 5 to 6 liters, females were 4 to 5 liters. So that means that we are pumping our entire volume of blood through the heart in 1 minute. So that's kind of amazing. And that equals up to roughly 7,000 liters of blood that we are pumping through the heart daily. So that is quite a bit. And remember, this is definitely going to change from individual to individual. Let's take a look, and of course circumstances, like this is going to increase during exercise. What about resting? So the main thing is we need to have the minimum amount or the resting cardiac output. We need to maintain this resting cardiac output of about 5 liters per minute because that's the amount that the tissues are going to need in order to survive. But of course, this is definitely going to be different from individual to individual, just like I've repetitively said, right? If you think about an individual that has a smaller heart, some females tend to have smaller hearts than males. Newborns are going to have smaller hearts than adults. They are going to have a smaller stroke volume. So if you have cardiac output, and that is going to equal heart rate times stroke volume, if you want to maintain it at 5, meaning that you don't want this to change at all, then these two are going to change. So if you have a smaller stroke volume, then what's going to happen to this heart rate? The heart rate is actually going to increase in order to maintain that cardiac output. So that's why newborns are going to have a higher a higher heart rate than adults. They have 120 to 160 beats per minute, and it's because of the fact that they're going to have a smaller heart and a smaller stroke volume because of that. Same with females. Because females will have a smaller heart, they tend to have a slightly higher, not as high as newborns, definitely not as high as newborns, slightly higher heart rate than males because of that. Now let's take a look at what happens with larger hearts. I'm going to go in and erase these arrows because it's definitely going to change with these arrows here. If we have a larger heart, then that means a larger stroke volume here. Again, we want to maintain, we want to make sure that we keep 5 liters per minute. With larger hearts, that means the cardiac muscle has hypertrophied, and that means that it can hold more volume. So that is going to increase. What's going to happen to this to maintain 5 liters per minute? It's going to decrease. It really depends on how large the heart is. It really is going to depend on how large the stroke volume is. Because if you look at a well-trained athlete, they are going to have an extremely low heart rate. It can be as low as 40 beats per minute. And it's because of the fact that they are going to have a higher stroke volume, and we need to maintain this 5 liters. Now, in reality, there's going to be some instances where we want to have more than 5 liters, right? We just talked about how we want more when we're exercising. We want to get more blood out to the tissues when we're exercising. So usually you will see an increase, but you don't want to see a decrease in that number. Because this is that resting basic cardiac output that you need, that your tissues are going to need. So let's take a look and see what happens with exercise and how that is going to change. I went the wrong direction. Here we go. All right, let's take a look at this interesting little graph that I have down here and see if we can make any sense of it, right? Right over here is going to be our cardiac output. And then we have oxygen consumption over here. So cardiac output, we're going to be taking a look at the line that is increasing with the work output during exercise, which means no exercise to a lot more exercise over here. Look at what happens to cardiac output. Remember, here's resting cardiac output, exactly what we would expect at 5 liters per minute. But as they increase the intensity of their exercising, look what happens. It goes all the way up to 30 liters per minute. Again, it's exactly what we need, because look at how much our cells are consuming oxygen whenever we're exercising. So in order to make sure that our cells have plenty of oxygen, we need to make sure that they have plenty of blood. So this is what oxygen reserve is called. It's by going in and subtracting cardiac output at rest from the output with exercise. And of course, you don't have to do all of that math. I'm not going to make you do that math. But if you think about it, if, again, cardiac output equals heart rate, it's a weird H, times stroke volume, if we want this to increase, which remember, sometimes we do. I know the last slide we were talking about maintaining it, but in this instance, we're looking at exercise. If we want to increase it, then usually you're going to have your heart rate accelerating. Everything you think is going to occur with exercising, right? Yeah, your heart rate increases, but so does stroke volume. Those two are going to work to make sure that cardiac output does increase. So cardiac reserve is just a good way to measure the level of exercise an individual can pursue. So for a non-athlete, such as myself, then healthy, I consider myself a healthy non-athlete, their cardiac outputs are it can actually increase 4-fold during exercising. With some trained athletes, it can increase 7-fold. So yeah, it can get quite, if you think about 5 times 7, yeah, it can go up to 35, even 40 sometimes liters per minute, which is outrageous, but it happens. So this, doctors can kind of use this measurement if you have a weakened heart. It's not able to pump that blood very well. So you're going to have little reserve, and you're going to have some limitations to exercise. So what we learned on the last slide is in order for when we're exercising and we need to meet the demands of our tissues, how does cardiac output increase? Well, we just talked about it. Heart rate accelerates, and so does stroke volume. So those are going to be the two key things that influence cardiac output. What we're going to be taking a look at are all of these, not only just exercise that's going in and influencing heart rate and stroke volume, but we're going to be taking a look at other things that will go in and increase or decrease heart rate, and how that's going to affect your cardiac output. I mean, really remember the main thing that we want to do if we are resting, we want to keep it at 5 liters per minute. We don't want it to drop any lower. So if it does start to drop lower, then our heart rate will increase. But there's going to be things that are going to increase heart rate or increase stroke volume. We're going to talk about how that is going to influence cardiac output. So there's several of these external factors that are going to influence heart rate and stroke volume, and in turn, cardiac output. So we're going to first take a look at heart rate, and then we're going to move over to this thing called stroke volume. So let's go ahead and introduce these variables that are going to influence heart rate. They are called chronotropic agents. So let's break this word down. Chrono. Have you seen that before? Chronological order, synchronized swimming. It has to do with time, right? And look, this is beats per minute. It's a time thing. Yeah, so that's how you can remember that chronotropic agents go to heart rate and influence heart rate. So we've talked about this before. We've talked about how there is something that is going to go in and influence and change heart rate. And that was going to be, look at that, autonomic nervous system, the autonomic innervation. So that's going to be one of the primary factors that go in and increase and decrease heart rate, and also certain hormones. It's always going to be either endocrine system or the nervous system. I say always, but you know there's always exceptions to that rule, right? So I showed that picture a long time ago, and it will creep up here in a second. But remember how it comes from the autonomic innervation from parasympathetic and sympathetic, and I showed how it innervated the SA and the AV nodes. We'll look at the chart here later. Let's first take a look at positive chronotropic agents. That means it is increasing the time or increasing the heart rate. Look at that. Remember that this came from the cardioacceleratory center down that sympathetic nerve path. We'll also take a look at some hormones here in a second and how it's going to affect it. All right, here's our little neuron. It's from the sympathetic division of the autonomic nervous system. It is going to release these very important neurotransmitters, norepinephrine. So norepinephrine binds to these receptors, key receptors here, beta-1 adrenergic receptors. And I want to mention these because we're going to talk about some medications that are going to influence this. As soon as it binds, look, it goes through this whole second messenger system. Look at the G protein, look at the CAMP. Don't have to worry about that second messenger technicalities behind this, right? What you need to know is that this, when the neurotransmitter binds to this beta-1 receptor, it is going to set off this whole second messenger system, and eventually this is what happens. It phosphorylates calcium channels. Here's the calcium channel right here. So it's going to trigger them to open. And what happens whenever they open is, look at what happens to calcium. Calcium is going to rush in. And technically what happens here is that the nodal cells are able to reach threshold quicker. That means that the SA node is just going to be able to fire at a higher rate. So that's what's happening here. That's why the sympathetic nerve stimulation is going to go in and increase heart rate. Anytime that heart rate increases, if stroke volume is not doing anything, then cardiac output is going to increase. But again, if the individual is trying to maintain cardiac output at 5 liters per minute, then stroke volume is going to decrease, just like we had talked about with the whole heart, the sizes of the heart. But let's take a look at hormones. Specifically, look at this thyroid hormone. Thyroid hormone goes in and pops in more of these beta-1 receptors all throughout the membrane. So it puts more right here, all throughout the membrane. What is that going to do? Well, that's going to stimulate this system more, which is going to stimulate more of this, which is going to go in and stimulate more calcium going in, which means it increases the heart rate that way. So it just goes in and makes more of these receptors available to happen. Let's take a look at some other things that are going to influence it. So those are the two big ones: hormones like your thyroid hormone and sympathetic nervous system. Let's take a look at some drugs. Nicotine. Nicotine is going to increase more neurotransmitters to be released, so it can go in and stimulate more of these receptors. That's how it works. Cocaine is going to inhibit norepinephrine reuptake. So remember, one way to get rid of these neurotransmitters is for the synaptic knob to suck it back in. So cocaine makes sure that norepinephrine is not sucked back in. It stays in the synaptic cleft for longer, which means it can go in and stimulate these receptors more often. So that's how it's going to work. And look at caffeine. It just works on this whole second messenger system. It inhibits the breakdown of cAMP. Don't worry about the little technicalities. Just make sure you know with caffeine, it can go in and increase heart rate. It's one of those that increases heart rate as well. If you drink coffee or sodas a lot or Monster drinks, then you know exactly what's happening with your heart rate. All right, let's take a look at the opposite that's occurring. These are going to be negative chronotropic, which means that it's going to decrease the timing of your heart or your heart rate. This is where your parasympathetic innervation is going to come into play. So what happens is acetylcholine is going to be the neurotransmitter, the key neurotransmitter here, and it binds to different receptors. It binds to muscarinic receptors. You don't have to worry about that if you don't want to. But eventually what happens is it causes hyperpolarization, and that just means that it takes longer for the cells to reach threshold. So it's harder for the SA node to fire at a regular pace. So it's going to slow the heart rate down. So that's how that works. And then beta blockers. Remember I told you, hey, remember that beta receptor. It's because there are some drugs called beta blocker drugs that go in, block this. So if these can't bind, then that means that heart rate is actually going to slow down. And this is a really good way to treat high blood pressure. So we will be taking a look at high blood pressure in the next chapter. So here's that chart that I wanted to refer to earlier that we looked at in a past video right there. Is going to be how that parasympathetic and sympathetic nervous systems go in and influence it. So the autonomic nervous system is going to influence heart rate through sympathetic and parasympathetic divisions through something called autonomic reflexes. So this is just going to be this reflex through the autonomic division. It's going to use the baroreceptors, the chemoreceptors. It sends signals to the cardiac center, and this is what's going to go in and alter or modify heart rate, and in turn, it is going to alter cardiac output as needed. So in the next video, what we're going to be taking a look at is the other variable, the other part to this nice little equation, right? And it's going to be stroke volume. So until next time.